So one of the uses of the linear model was to make comparisons across groups while controlling for other factors, right? So now that we know about accounting for the variability in the coefficients, let's see how that might affect our comparisons across groups. So we had many variants. Let's say we have, hey, only one group. We're just interested in estimating what's the mean for that group, some kind of constant C. Let's say we have a set of patients and we are interested in the average days to recover for those patients. That's just a constant we want to estimate. But normally what we have is two or more than two groups in an unpaired case. So that means we are comparing the mean of group A with the mean of group B all the way up to m different groups we have. And we do this comparison over different items or different subjects. So let's say we are interested again in the days to recover, but now we are comparing two different treatments, A, B, and potentially C, D, whatnot. And so what we have is different patients. That's why we say it's unpaired, because a patient number one in treatment A has nothing to do with patient one in treatment B. There's no relationship between them. And so we have one group of patients in treatment A, one group of patients in treatment B, another set in treatment C, etc., etc. And we want to compare the average days to recover across those different treatments. We can fit a linear model to control for things like the sex of the patient, the age, the surgeon, previous medical conditions, etc. And we do that with a linear model. So now we are going to test all of this. And what we're going to see is that those tests across groups are equivalent to testing very specific coefficients in a linear model. So if we do build a linear model, again, we're going to be able to control for these other factors. So we have two or many different groups in a paired case, for example, in which we do have the same items. We are controlling for the item, we're controlling for the patient, for example, or a student. Let's say that we are testing students before the course starts, maybe at midterm, and after the course finishes. And we have observations for every student. We have the pre-test and post-test, for example, for every student. This is a case in which we can use a linear model to see those differences between pre and post, while accounting for differences across students, while controlling for the student. Let's take a closer look. So let's start with the case of only one group, and we're interested in estimating the average. So let's say in this case, we have a certain amount of data. Here's a histogram showing us the distribution. And here this blue vertical line is the estimate we have in our model. So right over there, about 0.5. All right, conceptually, what are we talking about? Well, what we're saying is that the response Y is a function of basically nothing. We're just interested in the average of the response. We're not interested in a relationship between some other predictor and the response. So just the response. Let's set up hypotheses. How would we normally approach this problem? It would be null hypothesis. The mean in the population mu equals a certain constant that we're testing. Alternative hypothesis is different from the constant. What is the test statistic? Well, we saw it in the previous lectures. We have the observed mean minus the constant, and then we have the standard deviation in the response, and we have the square root of the sample size. Fair enough. So what do we have in this case? Well, the estimate in our case, in our sample data, is about 0.5. And here we had a test, a t-test. We were checking for c equals 0 in this case. This is the test score and the corresponding p-value of 0.003. Fine. So if we were able to just fit a linear model to this, it would be something like this. The response is just an intercept. And we know there would be a certain error term, right? So this coefficient, beta 0, would be modeling the average for the response. If we fit the model, then the regression table would look something like this. The estimate for that coefficient for beta 0 would be precisely what we had, the sample mean. We have a certain standard error, and we also have the t-value and the p-value corresponding to the hypothesis. We know again, beta 0 equals 0, or without the hat actually. And of course, those two tests are equivalent. The t-scores and the p-values are just the same. And so we see, this is because if we take a closer look at the test statistic, this sample average for the response is actually beta 0. That C is the constant we're testing against, which in our case is 0. And the whole denominator turns to be the standard error of beta 0, the standard error of the coefficient. So you see, testing for mu equal a certain constant is equivalent to testing for the intercept, in this case for beta 0. So we can see how this t-test is all the way equivalent to a linear model in which we test for the specific hypothesis beta 0 equals 0. It's exactly the same. What happens if we have two groups in an unpaired case? So we have group A and group B, and we're interested in checking for differences between them. And again, this is not a paired comparison. So items in A are unrelated to the items in B. So let's say we collected some data, and we have here in red and blue the two distributions we obtain and the two estimates. So we estimate A about 1 and B about 1.3, so to speak. What is the conceptual model we're dealing with? We're saying that the response is a function of the group. So the response is going to be determined by the group a certain item belongs to, A or B. Well, we could just do a t-test again. It would be something like this. The null hypothesis states that the mean in A is equal to the mean in B in the population. And the alternative hypothesis is, well, the means are different. The test statistic would be something like this again. So we have the observed mean in group A, the observed mean in group B, and the overall standard deviation in the response and sample size. If we were going that way, then we would find that the estimated mean for group A is about 1.1, and the estimated mean for the group B is about 1.6. If we compute the test statistic, it turns out to be 2.5, and the corresponding p-value is about 1%. So that would be a way to proceed to look into a problem like this. We could also fit a linear model, and in this case, our linear model would be something like this: beta 0 plus beta 1 xb. And this xb is modeling whether we belong to group A or group B. And so this is just a dummy variable. All right, what would be the regression table in this case? So we have beta 0, which would correspond to the average for the reference. In this case, the reference group is A. And the estimate is 1.083, which is exactly what we had earlier. The estimate for beta 1, which is the deviation from the reference beta 0, is estimated as 0.55. And of course, if we sum these two numbers, what we have is the estimate for the population mean in group B. We have the standard errors, we have t-values, p-values, etc. And if you notice, this test statistic is precisely the same as we had earlier. And of course, the p-value is also the same. So you see, what we're doing here is testing the hypothesis that beta 1 is equal 0. That's precisely what we were doing before in a simple t-test. Why? Because again, this mu for A is just beta 0. The mu for B is beta 0 plus beta 1. So we are adding the deviation for the second group. And the denominator is just the standard error of beta 1. That's it. So we see again, testing for this hypothesis, the mean of group A is the mean of group B. It's completely equivalent to just fitting this linear model and testing for this coefficient alone. It's exactly the same thing. What happens in the paired case? So for every item in the dataset, we have a score corresponding to treatment A and a score corresponding to treatment B, or something like pre-test, post-test. So now we could just make a scatter plot. So for every individual, here corresponds to 1 point, we have a measurement across A and a measurement across B. And what we're interested to see is, again, differences between A and B while controlling for the particularities of each of those items or persons. And so in this case, the estimate of A is again 1 and something, and the estimate for B is 1 and a little bit more. Conceptually, what we're saying is that the response depends on the group and the item. We're now going to control for the item. We could set statistical hypotheses all the same. So the null hypothesis is, again, the mean for A is equal to the mean for B. And the alternative is they're different. What would be, in this case, the test statistic? It's the same, only that in this case is the standard deviation of the difference between A and B. If we were ahead and just compute all the values, then we have these estimates, and we have the test statistic and the corresponding p-value. In this case, the p-value is 0.12. So in this specific example, we don't have enough evidence to support this rejection of the null hypothesis. We don't reject the null hypothesis. Again, that doesn't mean we accept it. It only means that we don't have enough evidence to reject it. So fine, can we approach the same problem through a linear model? Sure. So it would be something like this. Beta 0, which corresponds to a specific case for the first group, for group A. And then we have beta 1 xb, which is the deviation for group B. And then we have specific deviations for each of the other items, item 2, item 3, item 4, etc., etc. What does the regression table look like? Well, part of it looks like this. And of course, there's more coefficients down here for beta 3, etc., etc. But the important part is beta 0 and beta 1. Beta 0, again, models the specific case of item 1 and group A. And then beta 1 corresponds to the average deviation for group B. It's not for one specific item, it's for all items in general. So this number here, this estimate, is giving us the difference between group A and group B. And sure enough, what we have is the t-score and p-value the same as we had above. And this difference, 2.33, is exactly the difference between those two. And so again, this is another case in which fitting a linear model and testing a specific hypothesis is equivalent to, in this case, a paired t-test to compare between two groups. Why is that? Well, because here the numerator of the test statistic is exactly beta 1, and the denominator is exactly the standard error of beta 1. So we're doing exactly the same thing. Only difference is, in this case, beta 0 is harder to interpret because it corresponds to a specific item, but it doesn't matter. What we're really looking into is beta 1, which measures the average deviation between group A and group B for all items. And so there we go. We can use a linear model to make comparisons between groups while controlling for many other factors. In this case, it's only one factor, the item, but it could be many, many others. And we could start plugging more interactions into it, and again, look into very specific coefficients and test hypotheses about those coefficients. And this leads into what we call the analysis of variance, or ANOVA. We could have a full course on ANOVA. We're just going to simplify a lot in these few slides, but just to get you an idea of what we do here. What it does is get the whole variation in the response, the total sum of squares, and it's going to kind of partition it into how much of that variation is due to each of the factors that we are contemplating in the model. So what it does is actually quantify the amount of variability between the mean scores across each of those groups. So let me illustrate a little bit. Let's say that we have a certain factor with 4 levels, 4 categories. Let's say we have a certain distribution of scores for A, a certain distribution for B, then something for C, which is around there, and then D. If we are able to plot the mean scores for each of those groups, they will be here, 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 and here. Then what ANOVA is saying is how much variation do we have across those mean scores. In this case, there's a lot of variation. That means on average, those groups are linked to very different responses. We could also have something like this. A is around there, then B is also around there, C is around here, and D is around there. In this case, there is a lot less variation between the mean scores of each of the groups. And this is precisely what ANOVA is going to compute for each of the factors in the model. There's not so much variation here, there is a lot of variation in there. And this is an indication that the differences across the groups are, in this case, high, and in this case, the differences are low. And it also tells us that this factor in this first case is responsible for a lot of variation in the response. In this other case, it's not responsible for that much variation because they're not so different anyway. So ANOVA is going to look into these distributions for each of the factors in the model. And so, again, it quantifies the amount of variability that we observe in the mean scores for each of the levels of the factor, for each of the categories. And so if that variation is high, that means the groups are clearly different. This factor can explain a large portion of the variability in the response. If it's small, it means the groups are apparently not that different, so it's likely that the factor doesn't play a role in the response, that it doesn't affect the response that much. Somewhere in between, of course, there's many shades of gray. What matters is really the relative comparison between the factors. So let's look into an example. Let's say here we test hypothesis about the multiple groups of a factor, let's say between insurance yes or no in this first hypothesis, or between the different marital status in this other hypothesis. We have a model in which we included the age, the year, the marital status, and the insurance. So you see, it's not only those hypotheses, it's a more comprehensive model that we chose for whatever reason. Maybe we are sure that there's a certain effect of the age and the year, or we want to control for age and year when testing hypotheses about insurance or not. And we have the full regression table. How do we test here? Well, we might be inclined to say for this simple hypothesis of insurance yes or no, we go into coefficient beta 7. And this one here, this estimate is giving us the difference between insurance yes and insurance no. And we have a very significant p-value, right? How do we test hypotheses about the different marital statuses? Because it's not only two groups, it's many different groups. So we have to look into all these estimates, all these p-values. But wait, actually those are deviations from one case, which is never married. So how do we really come up with a way of testing hypotheses in such a case? Well, we can't do it directly from this table. We need something else. And ANOVA is going to give us a direct answer to this question. So what does the ANOVA table look like? It looks something like this. So now, first, the difference between regression and ANOVA tables. In this case, we don't have each of the individual coefficients of the model. We have each of the factors of the model. So we only have, for instance, for status, for marital status, we only have one row. We don't have one row for each of the different coefficients involved in modeling all the different marital statuses. We only have one. And so what this is telling us is each of the factors, how important they are for the response, or how much variation in the response are they responsible for. And that's what we can look at in these two columns. The larger the number, then the more variation they are responsible for. And we have, of course, attached p-values. What do those p-values test? Well, they actually correspond to this specific test, in which we have that in the null hypothesis, the means of all the groups in the factor are the same. This is what we call the omnibus hypothesis. So we are not testing for one specific case, one specific difference between, for example, married and widowed. We are testing the hypothesis that all of them have the same mean. And if there's only one of them that's different from the others, then we should expect this hypothesis to be rejected. And that's exactly what we're looking at in this ANOVA table. So again, the p-values test this specific hypothesis about all the groups in the factor being equal. And this part of the table tells us about somehow the importance of the factor. How much variation in the response are they responsible for?